In this video, we'll learn how to use definite integrals to compute arc length of curves. Here's a graph of the function f of x equals x squared, and we want to find the length of this curve between x equals 0 and x equals 2. We can get a rough estimate of the length of this curve by connecting the endpoints. The x and y axes in this graph are not on the same scale, but to get from one endpoint to the other, we go over 2 and up 4. So a rough estimate for the length of this curve would be square root of 2 squared plus 4 squared, which would be the square root of 20 or 2 root 5. In fact, we can say the length of the curve must be greater than the length of this line segment, because the line segment is the shortest path between these 2 points, and the green x squared curve takes a different path. How could we get a better estimate? We could add an intermediate point on the curve. The first line segment goes over 1, up 1. The next one goes over 1, up 3. So the length of our curve is less than the square root of 2 plus the square root of 10. We could keep going, adding more and more line segments, and before too long, the sum of the lengths of these line segments should be pretty close to the length of the curve. In general, we're approximating the length of the line segment by the sum of the distances of those line segments. The distance of each line segment is given by the delta x for that particular interval squared plus the delta y for that particular interval squared. In our example, all of the delta x's are the same, but the delta y's differ as we go from point to point. Based on our previous work, we suspect that this might be a Riemann sum. But with a Riemann sum, we'd expect to have a delta x over here. So let's make it happen. And then deal with the consequences. I can now bring this delta x up inside the square root by squaring it. We have this with our delta xk outside to make a Riemann sum. So simplifying, we get this. As k gets bigger and bigger and bigger, we suspect this will converge to a definite integral of this form. We're looking at a general Riemann sum here, so in general we'd go from a left endpoint to a right endpoint for x. But the question is, what does delta yk over delta xk, what does that become closer to as k goes to infinity? You may remember that this looks like something we discussed in differential calculus. We took a slope of a secant line and we took the limit as that delta x went to 0, and we got the derivative dy dx. There are some technical details we'll skip here, but in fact that's what happens in this case. So for our y equals x squared integral, the length of the curve should be the integral from x equals 0 to x equals 2, square root of 1 plus, well, we take the derivative of y with respect to x, we get 2x, square that, dx. We can simplify slightly, and now we just need to work out this integral. At some point we'll be able to find an exact value, but approximating this definite integral yields about 4.65 units. You can check that this is bigger than 2 root 5 and square root of 2 plus square root of 10 are rough estimates from before. Now let's look at a curve given parametrically. This is not a graph of a function, but it's a perfectly good curve, and it's given by x equals cosine of t and y equals sine of 3t for t between 0 and 2 pi. Once again, we can connect various points on this curve until we get line segments that do a very good job of approximating our smooth curve. Once again, we approximate the length of our curve by the sum of the distances as we go from point to point. This is exactly what we had before, except now we have functions of t. So when we do our wishful thinking, we want a delta t out here, and then we want to divide by a delta t down here. Moving the delta t inside the square root, we get this, which resembles a Riemann sum. And skipping a couple of the technical details, we get this integral with t going from our starting value to our ending value. For our particular parametric curve, the length of our curve would be the integral of the square root of dx dt squared. So that would be negative sine of t, quantity squared, plus the derivative of sine of 3t, which would be 3 cosine of 3t, quantity squared. And we have a dt, and our limits of integration will be from t equals 0 to t equals 2 pi. Simplifying this integral a bit, we get this integral, which will prove challenging even once we learn more advanced anti-differentiation techniques. So here we get an approximate value of 13.36.